dipole.
Okay. Okay, in our last class we have discussed about antenna theorems we completed. After that, fields from an oscillating dipole. Okay. What actually we have discussed in this topic? Fields from an oscillating dipole. What fields we have discussed earlier? Yes, anybody? What we have studied in this topic is very important topic for your examinations also. How the electromagnetic waves are coming from a simple dipole antenna. Okay, how the electromagnetic waves are generated or initiated, and how it is separated from the antenna, and how they are traveled away from the antenna. Okay, in our last class we have discussed this, right? We have seen how these electromagnetic waves are generated. Okay, because of the equal and opposite charges. Okay, they are in a simple harmonic motion. Okay, if these two charges they will move in this direction. Okay, this positive charge and this is the negative charge. Okay, because of this simple harmonic motion, the electromagnetic waves are these are the field lines. They are initiated, and okay, whenever these two charges they will cross each other. Okay, these electromagnetic field lines will be separated from the antenna, and it will travel away from this antenna. Okay, last class we have seen these things. Okay, a different time interval. Okay, here capital T is the time period of the simple harmonic motion. Okay, right? Here the positive charge is there. It will go here. It will take T by 2 times, and it will come back here. It will take another T by 2 times. Total is T by 2 plus T by 2. T capital T is the time period of dipole oscillation, or the time period of the these charges. They are traveling from the same position to here and again come back to this position. Okay, this is the time period. Okay, and we also discussed about the antenna field zones. Okay, what is this antenna field zones? Can anybody tell me what is this antenna field zones? What is the zone? Zone means what?
Certainly.
It is the some of you are not. You have mentioned your Sheikh. Who is Sheikh? You have not mentioned your roll number. Okay, please. Okay, add your roll number to your name. Okay, tell me. What is this antenna field zones? What do you mean by this? Okay, the surrounding area of an antenna is divided into how many zones? How many field zones? Zone means area. Okay, in a three-dimensional space, the area, the volume, you can say. Okay, in three-dimensional space, the surrounding area is divided into two parts. One is near field region, and other one is far field region. What is other name for near field region? Hello. What is the other name for near field region?
Fresnel region.
Fresnel region. Okay. Similarly, far field region is Fraunhofer region. Fraunhofer region is also called as the far field region. And also here we have seen the minimum distance. Okay, minimum distance means the far field region, the starting of the far field region. Okay, it will start at r is equal to 2d square by lambda. We are interested in this far field region. Here only we will calculate the electric field strength and also magnetic field strength, or you can plot the power radiation pattern or field strength radiation pattern. Okay, this is the minimum distance. Okay, we are not at all interested in near field region while designing these antennas. Okay, next topic here, this is the boundary sphere for this far field and near field region. This is the big sphere. Actually, this is a sphere. Similarly, yes. Okay, here this is our antenna. Okay, here what is D? R is equal to 2d square by lambda. This is 2d square by lambda. 2 into d square by lambda. Actually, this is okay. What is D? What is D?
Diameter or length.
Diameter of the antenna, or antenna means this is a boundary sphere. Boundary sphere or boundary sphere of antenna region, you can say. Otherwise, you can say this is the length of the antenna. Very good. Okay, these are the field zones. Okay, our and also we have solved these two problems, right? Last class, Mark, we have completed these problems.
Yes, sir.
Okay.
So,
Okay. Yeah. Today we'll discuss one more important topic. First, we'll see the types of dipole antennas, and after we see the important topic, basics of Maxwell's equations. We'll discuss one by one. Okay, first we'll see types of dipole antenna. Okay, dipole means we are having two poles, right? It has two conductors. Okay, generally these dipole antennas are classified into three types. Okay, you can say infinitesimal small dipole or Hertzian dipole. The other one is short dipole, and finally you can call as a dipole antenna. Okay, this dipole antenna we'll see one by one. When you call a dipole antenna, here we have seen that okay, it has some length. Based on this length or the diameter of this antenna, we can decide whether it is a Hertzian dipole or short dipole or dipole antenna, simple dipole antenna. Okay, first we will see the Hertzian dipole. Hertzian dipole or infinitesimal small dipole antenna. Here the length of the antenna is less than or equal to lambda by 50. If the length of the antenna is very small, then it is called Hertzian dipole antenna. Okay, normally this type of antennas are not useful. Okay, where these dipole antennas are normally used? Can anybody tell me where these dipole antennas are used? Okay, most of these antennas you can find out in these automobiles. Automobiles are carrying this type of dipole antennas. Hertzian dipole is a very small antenna. You can say it's a very it is very less useful. And one more important thing is the radiation efficiency also very less, and it has the losses. Okay, higher losses, and it has a larger region of refractive field. Refractive field is okay. You can say that. See, this is the boundary sphere of antenna region. Okay, here the inside that field is called reactive region. Okay, for this Hertzian dipole, okay, the reactive region is very high. Okay, and this type of antennas in real time, we are not using this type of antennas. This is for theoretical purpose only. We'll study this type of antennas. Next one is short dipole. Short dipole antenna. Here for the short dipole antenna, here the length of this antenna varies from lambda by 50 to lambda by 10. If the length of the antenna falls in this region, in this range, okay, then we call the dipole antenna is a short dipole antenna. It is also less useful. Okay, compared to the Hertzian dipole, the radiation efficiency is a little bit high, but this is not enough for our practical applications. The radiation efficiency is, you can say, in practical application, this is less, and also losses also high. Okay, refractive region of refractive field also very high, and also it has a very few applications. Okay, next one is okay dipole antenna. In dipole antenna, the length of this the length of this antenna is lambda by 2. Okay, this is also called as half wave dipole. You can say if the lambda is if the L is equal to lambda by 2, we can say simply you can say it is a dipole antenna, or you can say half wave dipole. Why? Lambda is the wavelength. If the wavelength divided by 2 means half wave dipole. Here I will write this thing. Okay, if L is equal to if L see if L is equal to D by 2, if L is equal to D by 2, okay, it is also called as half wave dipole. Half wave dipole. Why? Because half wave. It's a half wavelength. This meaning is half wavelength. Okay. Otherwise, I will write here. This is half wavelength. Okay. If the length of the antenna is half of the wavelength, then it is called half wave dipole. Okay. Suppose if it is lambda by 4, if the length of the antenna is lambda by 4, then that type of antenna we can say it is a quarter wave dipole. Quarter wave. Okay, quarter wave dipole. Here in this quarter wave dipole, here the length of the antenna is lambda by 4. Okay, these are the two popular antennas. Even though the length is lambda by 4, okay, it also offers a very good radiation efficiency, and almost it has the radiation pattern also similar to the half wave dipole. This is the half wave dipole and quarter wave dipole. They are popularly used in automobile applications. Okay, it has a maximum radiation efficiency in this category. Okay, in this dipole antenna category. Okay, these are the three important dipole antennas. Okay, in practical applications, dipole antenna is used. Okay, we'll discuss this dipole antenna, okay, half wave dipole and quarter wave dipole antennas in details. Okay, in coming lectures. Okay. Our next important topic is Maxwell's equations. Okay. You know the historical background of these Maxwell's equations. Okay. Maxwell's is a scientist. Okay. He composed all the electromagnetic theories. Okay. And he proposed 4 equations. By using that 4 equations, we can able to represent electromagnetic wave fields. Okay. Okay. Here, okay. Here, Maxwell's equations are necessary to understand the existence of electromagnetic fields around a current. Yes. No, somebody having any problem?
Sir, I have a doubt, sir.
Tell me.
Sir, dipole antenna, for which purpose?
Hello. Dipole antennas are used in automobiles lo use chestam manam. Okay, automobiles ante cars lo gaani vehicles lo vaati use chestam. What is your question? Hello. Okay. Maxwell's equations are necessary to understand the existence of electromagnetic fields around a current carrying conductors. Okay, these are the 4 equations that proposed by the Maxwell. Okay, these equations you are very much familiar. Okay, you have studied in your electromagnetic theory. Okay, what is the first equation is called? Can anybody tell me? What is this? Del dot B is equal to 0. What do you mean by this? del dot B is equal to 0. Can anybody name that equation? What is that equation? Emma, you cheptara? What is that equation? Del dot B is equal to 0. This is the divergence of the, what is the magnetic flux density? Okay, the divergence of the magnetic flux density is equal to 0. Okay, what is the name of this equation? Can anybody tell me? What law it is? Cheptara evarana?
Gauss law.
Yeah, Gauss law for
sir.
Gauss law for magnetism. Here, these two equations, first equation and second equations, they are the Gauss laws. First one is for the Gauss laws for magnetism, and this is the Gauss law for electricity, the electric field. Okay, and what is this third one? Del cross H is equal to J plus dou D by dou T. What is this H? And what is this E? What is E? Capital E. Okay, I will ask we will discuss each and everything, and all units also you can discuss here. Now, anybody tell me what is capital E and what is H? What is this equation? What is this equation? Del cross H is equal to J plus dou D by dou T. Tell me, what is this equation? This law, what is this law? Anybody in the class?
Ampere's law.
Very good. This is Ampere's law. Ampere's law. And this is del cross E is equal to minus dou B by dou T.
Faraday's law.
Faraday's law. Yes, right. Okay, here this Ampere's law says that, okay, we'll discuss in detail in coming slides. Okay, the del cross H, here the Ampere's law says that if there is any magnetic field, okay, time change, that magnetic field will produce electric field. Here D. Okay, what is D? What is D? This is magnetic flux density. This is electric flux density. You can say
Electric field.
Okay, similarly, okay, here this is the Faraday's law. Faraday's law saying that if there is a change in the electric field, it will also change in the electric field will induce magnetic field. Okay, there is a relationship between electric field and magnetic field. Okay, ma, in 10 minutes our session will close. Please try to rejoin the class. Okay, these are the 4 essential equations to understand the electromagnetic fields or electromagnetic waves. Okay, here you see these terms. You have to understand the units of these Maxwell's equations. Capital E is called electric field or electric field intensity. The H is called electric field strength or electric field intensity. This is volts per meter. And H is called the magnetic field strength or magnetic field intensity. Okay, this is amperes per meter. And D is called the electric flux density, and B is called the magnetic flux density. Electric flux density, this is coulombs per meter square. Similarly, magnetic flux density, Webers per meter square. Similarly, J is called the current density. J is called current density, amperes per meter square. And Q is called, here sometimes they are represented by rho. This is charge density. Actually, this is not Q, rho actually. This is charge density. Charge density means coulombs per meter cube. Okay, here this is rho. Del dot D is equal to rho. The divergence of the electric field, electric flux density is equal to the charge density. Okay, you will get the charge density. Okay, we'll discuss one by one. First one is Gauss law. Gauss law, yes, Gauss proposed 2 laws. One is Gauss law of magnetism. The other one is Gauss law of electricity. Okay, Gauss law of magnetism says that magnetic field lines are always a closed lines. What does that mean? Can anybody tell me? Magnetic field lines are always a closed lines. How can you say that it is a closed lines? Okay, can anybody tell me? Actually, in a magnetic field, if you take a magnet, Okay, we'll say that in a magnet there is a south pole and there is a north pole. Okay, if you divide that magnet into two parts, again you are getting south pole and north pole. Okay, generally if you divide that magnet into equal amount, half like that, okay, you can find a very small amount of the magnetic material. Okay, there you can say that there is no kind of a south pole and north pole. Okay, it acts as a dipole. That magnetic material, it acts as a dipole. They're saying that, okay, there is no starting and ending. There is no starting and there is no ending. For that reason, magnetic field lines are always a closed lines. Because of that reason, the divergence of B, we'll see this, what is this divergence, what is this curl, and what is the gradient. Okay, how we want to calculate these gradients. Okay, in a short moment, we will discuss all those things. Then only we'll proceed further in this subject. First of all, I want to give a glimpse of these Maxwell's equations. Okay, Gauss law of magnetism says that the magnetic field lines are always a closed lines. Here we can say that normally we'll say that there is a south pole and there is a north pole. Okay, in practical you can say that, okay, there is no such north pole and south pole. If you divide that magnet into small poles, okay, it will have the south pole and north pole concept. Okay, they appears as the north pole south pole undanukuntam gani, but it acts as a there is no such of south pole or north pole and undadu anamata. Okay, it is a continuous circle laga untadu anamata. There is no ending. That's why the divergence of this magnetic flux density is always equal to 0. Similarly, okay, in Gauss law of electricity says that in electricity we can say that there is a positive charge and negative charge. Because of this positive charge and negative charge, they will appear. Okay, here the divergence of this electric flux density is equal to the charge density or electric field density. Okay, charge density, you can say this is not equal to 0. Why? Because in electricity we are having positive charges and negative charges, and clearly we can separate them. Okay, that's why the divergence of this electric flux density is not 0, but here it is the charge density rho. Okay, you have to understand these two things. Okay, even though we say that there is north pole and south pole, but in practically there is no south pole or north pole concept. There is a continuous lines, okay, in a magnetic field. But in electricity we are having positive charges and negative charges. Therefore, the divergence of the electric flux density is not equal to 0. Okay, here it is rho, that is charge density, coulombs per meter cube. Okay, you have to remember this. Okay, here the D also called as displacement electric field density anukuntam manadini. Here B is called magnetic flux density. You can call D as a electric flux density. It is also same. Okay, you have to understand this terminology. Here B is called magnetic flux density. D is also we can call it as a electric flux density. You can, no problem. Okay, okay, D is also represented as a displacement electric field density. Displacement electric field density. The units for D is coulomb per meter square. Similarly, for magnetic flux density, the units for magnetic flux density is Weber per meter square. Okay, this is about Gauss law of magnetism and Gauss law of electricity. Okay, next one is Faraday's law. Okay, Faraday's law, the curl of the electric field intensity or the electric field strength. Okay, del cross E is equal to minus dou B by dou T. What is B here? B is the magnetic flux density. What is E? E is the electric field intensity. Electric field intensity or electric field strength. Okay, whatever we are discussing in the radiation pattern. Okay, there we are using the E, right? This is the same E here. Okay, here del cross E is equal to minus dou B by dou T. Okay, what does it mean? It is the changing magnetic field. dB by dt is the changing magnetic field or changing magnetic flux density creates electric field. That meaning of this relationship is that the change in the change in the magnetic flux density will always create electric field. This is called Faraday's law. Faraday's, okay, he find out the relationship between what is the if the magnetic flux density is changing with time, okay, it produces electric field. Okay, he identified and he proposed this this law. Similarly, Ampere's also proposed another theorem. Okay, it says that, okay, if there is a change in the electric field intensity or electric flux density, okay, if there is a change in electric field, it creates the magnetic field. Okay, here there is another way of generating the magnetic field by simply changing the electric field with respect to time. We can able to generate magnetic field. Okay, here H is called magnetic field intensity. And what is this J? J is the conduction current density, or you can say current density, simple current density or conduction current density. These I am not going in details. Okay, whatever is required in this course, okay, I will discuss. Okay, it is Ampere's law. Apart from all these four Maxwell's equations, okay, the following identities also used in determining the potentials. Actually, we want to find out the static potential and vector potentials. Okay, we'll see in short time. The three identities that are used in this EM wave equations is, one is D. What is D? What is D? D, what is D? Electric flux density. Simple, you can say electric flux density. What is E? Capital E. What is capital E?
Electric field.
Electric field intensity. Electric field intensity. Here, what is this? What is this? Epsilon. What is this epsilon? This is the permittivity of the medium. Permittivity of the medium, whether it is a free space or it is a different kind of medium, right? Similarly, B is equal to mu into H. What is B? What is B?
Magnetic flux.
Magnetic flux.
Yes, magnetic flux density. Magnetic flux density, this is electric flux density, is equal to mu times of H. What is H? What is
Magnetic
H?
field intensity.
Magnetic
field.
Yes.
Field intensity.
Yes, this is magnetic field intensity. This is electric field intensity. Okay, the relationship between the magnetic flux